been doing oscillations, getting ready to do waves, but oscillations themselves are good. We use springs horizontally, vertically, pendula. Here's a spring going up and down. We can model it pretty much as simple harmonic motion. Eventually it's going to die out though, isn't it? So it does eventually die out. It dies out by friction. What we're going to look at now is, you should know the simple harmonic motion equation, the ideal case of Newton's second law, where the force is linear and restorative, meaning the force always brings you back to equilibrium. So if you're stretched, it'll bring you back. If you're compressed, it'll push you back out. Right? But restoration with a pendulum, force of gravity brings you back. And you coast on through, and then force of gravity will bring you back. And we did that using torque. So now we're going to just add a little bit to the mix. This is introduction, a little taste. Keep in the back of your mind that this has multiple purposes, not just mechanical. Electrical circuits have very similar equations, and oscillations on top of moving give you waves. So those are just some of the great applications. You need to learn your mathematics and put that together with your physics. So we're going to do the case of fluid damped oscillations. It would be a simple harmonic motion, so I set this case up for simple harmonic motion, but I've got fluid damping. They're often just called damped oscillations, and sometimes they say friction. What we really mean is fluid friction or drag. Why do we do that? It's a setup. We're making the math straightforward, easier. You remember when we approximated sine theta as theta in radians when we did the pendula. Similarly, we're going to set it up. When you're learning, you don't want to get into too big a mess, and you might not ever need that. So for this case, we have force drag as a simple model of fluid friction where it's negative some factor times the velocity. Stick your hand out the window as you move faster. Your hand moves faster through the air or through water. You'll feel more drag, obviously. We can write velocity as the second derivative position with respect to time. Just pause though. B. What are the units of B? So whenever you see something new, that should be a habit now. B. Oh, that's newtons divided by meter times second. I'm doing that in my head. Let's see, B would be in newtons divided by meter per second. That's newtons times second over a meter. That's a kilogram meter per second squared. That's my newton times a second. Okay, that's cool. Divided by a meter. Did that work out? What is that? 1 over m. 1 over m. Huh, it's in kilogram per second. Does that work? Kilogram per second, kilogram meter per second squared. Newton. Cool. All right, I just got used to it. Don't have to memorize it. I know I can do that, but I can do it faster now. I'm more fluent with it. Conceptually, that's just your hand going through water faster, more drag. Okay. More complex models will have different powers of velocity. So we're just going to throw that in with our good old Newton's second law. We got a spring force, and now we're going to have this. We'll see what it looks like. Then we're going to get acquainted with fluid damped motion, simple fluid damped motion, and a sinusoidally driven oscillation. That is sinusoidal force, where the force is sinusoidal. Why? Because the math is nice and easy, and it provides a mathematical basis for doing any variety of situations. So it would be simple harmonic motion, but now it's an oscillation that's not simple harmonic motion. What is it? What did we learn? So in this case, with the driving force, we're going to throw this into Newton's second law. The driving force, or the external force is a nice way to put it, is the maximum force, external, times whatever, sine or cosine. You know, you can shift the sine or cosine with a phase constant. You can write this as omega external. Oh, see that? I forgot my t. It's a function of time, isn't it? That makes sense. Whew. So that's omega t. Right. Or 2 pi over the period, however you want to write it, right? But let's see what happens. Okay, let's do this. First, let's do the math, and we'll come back and check it out. So the method is, write Newton's second law, use an ideal spring with a force of negative kx. We know that in that case, just negative kx equals ma. Negative kx equals m d squared x dt squared, right? When we do that, pops out omega of the oscillation, angular frequency, is root k over m. That's also 2 pi f or 2 pi over t. Good, we're getting used to it. So just do that, but now we got some new forces. We're going to throw them in there. That's all. Then we'll choose a solution form that fits what happens. We do this in differential equations a lot. That seems like it's cheating. You're looking for, you get guessing the answer, but you're guessing the answer because you know the character of the situation. You know how it's going to behave. So you take one of these solution forms, put it back into the general Newton's second law, which is now a differential equation, and then you solve for the constants for your specific case, and that's how you do this. So let's do it for this, the case of a fluid-damped oscillation. Okay, so come over here and take a look. Let's think of it. So this oscillated, and by the way, it had died out by the time we came over this. So clearly it does die out. This is going to oscillate. And if I drop it into water, so it's fluid-damped, and I make it oscillate, if you can see that, it'll oscillate, but it won't keep going very long. So it'll oscillate back and forth a little bit, but notice the amplitude. What happens to the amplitude of the oscillation? All right, you get a few wiggles in there, and I am touching the surface. That's a solid-to-solid friction, right? I don't want that. I just want my fluid, because what happens if I put a solid friction, constant friction in there, right? It's independent of the velocity. Well, it's just, you can do it. It's just the math is a little different, right? And it's a little harder for us to think about. So anyway, it's good. That's what it does, right? All right, we'll come back to you. Let's do this problem. So here we go. Let's set up, what are we going to do? We're going to write Newton's second law. Fine. Follow my procedure. The first time through is always the shortest, the longest, the most awkward. So I'm going to write F, the sum of all the forces. This is 1D, so I'm not going to make much ado about it now. The acceleration is the rate of change of motion, dv dt, or dx tt squared. So that's just the acceleration. That's not a force. You know that. That's not a force. There's the forces. These are the things that make it happen. What are happening? Well, I got that spring in there, right? Negative k. You can just write x if you want, but I like us to remember that this is varying with time. So negative kx, there's a spring force, right? Heck, let's just keep it easy. Spring, ideal spring, plus what? Damping, right? I don't know. I hesitate. You'll see why. Friction, damping, whatever. We have a driven force, so I don't know if I want to put D in there. You just think about it, right? What is the? That's it. That's all I got. I got a spring. Now, yes, that was vertical. There is the force of gravity. When I put it on there, the force of gravity was balanced by that little stretch of the spring. And so throughout the oscillation, that extra stretch is always compensating for it, balancing, and you'd see it mathematically. So we don't need the mg in here, even if it's vertical. So I've got the negative k, x as a function of time. And what is that? Well, that's opposite the velocity. But wait a minute, is velocity changing with time? You bet. So I can go negative k, some function of time for position, minus the b, which is the damping constant. Well, you know the units. This has got to be newtons, right? dx dt equals that. Now everything's in terms of this unknown x. Now you can just leave it. That's kind of nice. Here's the spring force, here's the damping force, and here's what happens, the acceleration due to that. There's the resistance to the acceleration, right? But we often rewrite this. And so this is just algebra, not a big deal. Like I can move it over to this side, and I could say d squared x of t dt squared times, yeah, and that's going to be a negative, but they're all going to be negative. And that'll equal 0. So can I make it positive? Is that okay? Yeah. Think of it moving it there, flipping it over here. All right, plus b d x as a function of time dt, that's the velocity, plus k x as a function of time equals 0. Phew. All right, I think I got that right. Correct me if I'm wrong. I know in the last video I had 2 pi over f, and it should have been 2 pi times f because I was thinking 2 pi over t. F is, so you caught that, I hope, at the very end, close to the end. So what's that? Well, here's something else that we do. We just divide it all by m. I hope you don't mind me using the magic of dry erase. By the way, they make recyclable dry erase pens, so we're getting them. I highly recommend it. Eco Smart World, I think, was the place. I'm going to divide by m. So I got this constant, b divided by m. K, ooh, wait a minute, divided by m. Hey, omega, simple harmonic motion, or 2 pi f, or 2 pi over t, is root k over m, when it's allowed to just think. So that's there, but this guy is adding something. So my question is, what's the solution? So you see, it's easy. There's too many letters. What happens if your brain is going, memorizing steps, memorizing letters? Here's the steps. Then you just do it. The question is, what's the solution? And so we go back to our plan. Let's see, what have I done? I've written Newton's second law. I did rearrange it to make it nice. I need to choose a solution for them. So let's explore these guys here a little bit. Here's my equation of motion, where I kind of move my MA over here with the forces, and then I divide it by M. So the meaning is not nearly as transparent here. Here I can say I got a spring force, I got a fluid drag force, and this is not a force, it's MA. And I rearrange just so for mathematical purposes. So that's what I've got. Now, exponential growth, that t equals 0, that's 1, so it starts out at a, and here's going to be my x as a function of time, and this will be time, and it's going to grow. That means that it would take off exponentially. Now that works for biological systems, things that grow, but that's not going to work. And in general, for our physics, you know, you're really not going to expect to see exponential growth on an oscillation. That would be interesting. All right, let's compare that. Let's just do this over here. So I got rid of that guy. Let's do exponential decay. Again, t equals 0. E to the 0, anything to the 0 is 1. So it starts out at a, but I'm going to put it up here, a, and it's going to exponentially die out, right? I pull it, and then it's just going to fade. And physically, the motion is along here. Right? Dies out. Mathematically, it would take an infinite time. Physically, it wouldn't, so our model breaks down a little bit there. But I saw it oscillate a little bit. So we'll check that out in a second. Let's see the next one. Oh, wait a minute. If that oscillates sinusoidally or cosinusoidally, that's simple harmonic motion. I know what the answer is for that particular case, and I know what it's going to look like. It's going to look like this. T, x of t, imagine it to go like this. Here, let's see, where do I start? At t equals 0, that goes away. But it depends on that. That's all that does is it shifts where you are at t equals 0 and what the velocity is at t equals 0. Anyway, let's just say that's 0, whatever. And then I have, oh wait, excuse me. T equals 0. Make that 0. Cosine of 0 is 1. Let's start it here. A. But then what's going to happen is it's going to go down here from A to negative A, and, you know, go back and forth. So physically, it's going to go like this. My graph will go like that because this is the time axis, but physically, it'll keep on going with simple harmonic motion. We know the frequency, we know the period is from here to here on my time axis, right? All right, cool, but that doesn't do that, it dies out. So I'm not a big fan of this. Wait a minute, what does this function do? It oscillates but it has an exponentially decaying amplitude. How would that look? That would look like this. Let's just choose that phase constant so that we start out here at A. Here's negative A, but we never make it. It's going to oscillate, so physically it's going to start out here. It's not going to make it. Less, 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 right? And so what we have is our mathematical envelope of A e to the minus t over some constant, that tau. Now I mentioned it up here, that tau, you can't have, I mean, to say x squared means x times x. What does x to the 2 seconds mean? Or 2 minutes, or 2 inches, or it means nothing. You can't have any units in the exponent. So you've got, sometimes you see math, e to the t, that doesn't make any sense. You've got to get rid of the tau, of the units of time. Tau is a characteristic. What does it mean? Well, at t equals 0, you've got e to the 0, which is 1. At t equals tau, that's e to the 1. Okay. Here it'd be 1 over e to the 1. E is about 3, right? It's 2.7. Anyway, it's going to decay. So in reality, it's going to go like this. It's going to go. All right? Does that fit? Yeah. That's going to be my choice. And an exponentially decaying amplitude with an oscillation. What do I do with that? I take that. It's going to be a mess. You got to take the derivative once, put it in there. You take that, put it in for x. Take the derivative once. Okay, you got this product rule. You got a couple of terms. Get some paper out. Then you take that, you got 2 terms, and take the derivative again. Each of them is going to have 2 terms, right? Product rule. Good news. If you do the messy, ugly stuff, it whittles down to some fairly nice stuff. Now you can look at that and see what the frequency of oscillation would be when you do that. So that's the game for a fluid damped oscillation. Let's go over here and take a peek. And so here it dampens out. Okay. Put more mass on here. And what that does is really I'm looking at the surface area because I want more damping. Now I could do it in molasses or honey, that's going to be a lot of damping. But because it's got more area, like your hand grabbing air more this way than this way, it does oscillate. I do get that cosine oscillation, but it decays much more rapidly here. I can adjust that with the type of fluid. I can adjust that with the surface area. Here, I'm going to do this. I'm going to have to lift it up. Whoa, way up. All right. This guy's got a lot of area. Watch this. Ooh. Didn't even oscillate. Okay, so doesn't oscillate. So I've got 2 cases. One where I have an oscillation with a decaying, exponentially decaying amplitude. I choose this solution. And another where it just dies out. And so I'll leave that for now for your differential equations, but you can use that as actually the sum of a couple of terms here. Sort of an exponential decay. So you have an idea and you have the math. So you combine the general form with Newton's second law rearranged for mathematical convenience, and you've got that. Okay, so that's all that is. Keep it simple. Look, you know, just two forces equals ma. How easy is that? But now you've got a little differential equation. You've got just a few to choose from here that make sense. And you're good. Okay, cool. Let's try it again. What are we going to do now? I don't need to do this. Because I wanted to do a damped, I want a spring. I want it to be damped, but I want it to be driven. So plus F external, or driven. But that's going to be sinusoidal. So I take that mess and I put it right in there. So it's pretty similar, except I got another term in here, right? And then you can solve it. Again, with a differential equation, of course, you can look into that specifics. You can look at solutions and kind of study those solutions. So let's explore that. In other words, I'm going to drive that. Let's explore what you would do now with that. Just a little taste of this, some terms that are really useful to know. What we often draw is a response curve. Now, this is not the time axis, because you can drive it at different frequencies. Right? No matter whether the system that you're pushing likes it or not. So you can put frequency. Now I'll put frequency, right? And this is external, just so you don't confuse it. I don't know. Whatever. Or I could put period. You know, right? Because we know the relationship. 2 pi f is omega, 2 pi over the period. Fine. Hopefully that's drilled in now. So that means I can push and pull at whatever frequency I want. But the system, if I didn't have all this going on, would oscillate at its simple harmonic motion frequency. And so with that, what I've got is the natural frequency that the system would like to swing at. If someone's on a swing and you're pushing them, usually you push them, they come back to the top, you push them. They come back to the top, you push them. So you push externally at with the same period as the natural oscillation. That's how you're going to get them to, try to get them to go up and around the swing set. Right? But there's damping, so you never quite make it and get your friend to do the loop-to-loop to you. But that's the best. If they're coming towards you and you push, you're going to slow them down. So you slow them down, they swing. And then if you happen to push with their motion, you'll speed them up. And if you push against their motion, you slow them down. That's a principle we've been looking at all semester. So if your oscillation's not in sync with theirs, well, you can push against the motion, slow them down, then push with the motion, speed them up, make them go higher, and make them go less, and make them, and it's kind of jumbled. So what happens if you push at too slow a frequency, you don't get much of a amplitude of oscillation. So maybe it's here. As you get closer here, you get a better response. This is our response curve. If you push too fast, you also, sometimes you're pushing against, sometimes you're pushing with. And then you push closer, you get a better response, more amplitude for your oscillations. Here is where you get the maximum response or amplitude. And that is called resonance. And so we often will see this curve. Right? Now, given a particular system, if you have more friction than your friends on the swing, if you have more friction, you're still not going to get them to go up very high, but you know that the best you can do is to have omega external, or driving, match omega natural, or simple harmonic motion. That's when you get. And what do you get? You get the maximum response, or the maximum amplitude. So you can push at any frequency, higher or lower, you're not going to get as good a response or as big a response as if you do it the natural. Did?
No, yeah.
Okay.
Almost.
Like how many?
Probably a minute or
Okay, cool.
less.
So that's what resonance means. Push it to natural. If you have more friction, though, you're still going to get the maximum response, but not as much. More friction? That's that B factor, okay? So that's that. Now, what you get as you do this, you can do 3 cases. Let me get this up here real quickly. Okay, so that friction can affect, now without the driving the force, we can talk about this damping, just damped. So that damping effect can be this. Here's x of t, here's t. It's critically damped. Oh, excuse me.